All right. Greetings, wonderful people. So we're going to do something a little bit different today. We're going to be going over the homework. So this is going to be going over homework Unit 4, homework 10 is what it's called. So I'm going over this today because of the situation we find ourselves in. I know that students oftentimes have trouble with word problems, and these problems are kind of advanced, and even when I have students that I can work with in class, it's still quite a hassle to get these down. So you know what, let's go ahead and I'm gonna help you guys out on some of this here. So let's go ahead and jump into question number 1. There'll be no objectives today. We're not really working on any lesson today, just generalized learning. All right, so a pumpkin is launched directly upwards at 72 feet per second from a platform 20 feet high. The pumpkin's height, h, at the time, t, seconds, can be represented by this equation. Find the maximum height of the pumpkin and the time it takes to reach this point. So there's two things we're looking for here. So we're looking for maximum height and time it takes to reach this point. So not time in flight, but the time it takes to reach the maximum height. So I'm going to go ahead and create a drawing, because remember that was one of the things that we were, we talked about when we were, let's see, I'm going to just review some of the strategies really quick. So remember, familiarize what is being asked, and some of the strategies you can use for that is to draw a picture. All right, so we did underline some clues. We know what we're looking for. We have a much better idea of what we're looking for. We're looking for these two things here. All right, so it says launched upwards at at 72 feet per second. So that 72 is already in the equation because that is the upwards velocity. Don't forget, this is gravity, velocity, and how high the platform is. So in this case here, it says the platform is 24 feet high and it's already in the equation. So we don't need to modify our equation at all. So the equation's ready to go. We don't need to do anything, and these top numbers are just part of the exposition. So just another quick thing. Every word problem has 3 parts: the exposition, and what I call the clues or clue statements, and then the question. Now, some of them are a little bit different. Sometimes they will mix it up a little bit, but nearly all word problems will have this sort of order. So exposition, it's telling us a pumpkin's being launched, and it gives us a few clues as to how to set this up, but we don't really need them because it's already set up. And just to help you understand, I'm going to go ahead and draw a picture. So it says here a platform 24 feet high. So I'm going to just draw a little platform. And I'm going to go ahead and put a little 24 number right here. And it's launched upwards. So maybe I'll draw a some kind of device to launch the pumpkin. There you go. So that would go something like this. That would be the path that it would take. Well, if it was also launched a little bit sideways. Okay, so find the maximum height of the pumpkin. So what we're looking for is right here. And we don't even need to draw all this, okay? So even if you were to just draw a basic square, ground, and basic parabola, this question means we are looking for the vertex. So the vertex is on the axis of symmetry. So axis of symmetry formula, I'm going to just go ahead and put AOS for axis of symmetry, is negative b over 2a. And we already have our formula, our function set up already, so we don't need to change, really we don't need to change anything. So just plug it in. So in positive 72, but remember when you plug it in, the formula says that we need to change it so that it's a negative, or basically if it's a negative, it'll change it to a positive. Basically, you just reverse the sign. And over 2a, so in this case, 2 times negative 16. There we go. So now we kind of have a better clue of where the axis of symmetry is. So this is going to be negative 72 over negative 32. And I'm not sure what exactly is we're going to get from this. I'm going to go ahead and jump over to the calculator. And let's go ahead and type in. So we had negative 72 over negative 32. So that means it's a negative divided by a negative, which means it's going to end up being positive. So I already know my answer is going to be positive. So I'm going to ignore the negatives because this calculator is not really the best calculator. I can't punch in negative numbers. I can, but it's a bit of a chore. But anyway, it's pretty easy for me to keep track of whether it's going to be negative or positive. So it's going to be about 2 1/4 seconds, or 2.25 seconds. So we know that the pumpkin reaches the maximum height at 2.25 seconds. And that is actually one of our answers. Because it says time to reach that point. So we know it's 2.25 seconds, but we also want to find the maximum height. Where was the pumpkin at 2.25 seconds? So easily enough to figure that out, we just plug it back into the original equation. So negative 16, 2.25 squared plus 72t, but again, by plugging 2.25 into the function, into our formula or equation, we are asking the function, where is the pumpkin at 2.25 seconds? Because we know when it's at the maximum height, but now we want to know where is the maximum height. All right, so I'm going to go ahead and go back to the calculator and let's punch a little bit of this in. So I have 2.25 squared. So I'm going to punch in the square button and we get a number slightly higher than 5. Now, looking at the formula, we're also going to have to multiply it by negative 16. But again, my calculator is not the best. So I'm going to have to multiply it by positive 16 and then remember that it's going to be a negative result. So in this case here, it looks like we get 81. So negative 81 plus, and then we have no negative numbers here, so that should be an easy one to cover. So 72 times 2.25, and we get 162. Plus 24. And from here, we can go ahead and add all this together. And I'm just going to go back to the calculator really quick. 162 plus 24 minus 81. And there we go. We have our final result. So that's going to be 105 feet. Jumping on back over to the assignment. And again, let's see. Don't forget, okay, so we familiarized, okay, we drew a picture just to give ourselves an idea of what we're looking for, because, you know, there's a lot of different things you can be looking for. You know, total time flight, domain, range, maximum height, time to maximum height. There's a lot of different things that we could look for, but you got to know which one we're looking for. Okay, we didn't really need to translate anything because we already had a formula. Let's see. We didn't really need to solve it, but we did have to plug some things in and substitute it and evaluate it. And let's see, check it, does it make sense? And lastly, state your answer in given units. So we saw that it was 105 feet. And let's go ahead and be a little bit more descriptive and say that was to the maximum, 105 foot maximum. And let's see, let's ask ourselves, does that make sense? So if something is launched upwards at 72 feet per second from a high platform, does it make sense that it would reach you know, the height in about 2 seconds? And that would be about 100 feet. All right, so I know this is a little bit of a different type of problem, but I'm guessing that this is actually, I've heard of something like this before. Okay. This is one of those other things that we're talking about. I don't know if I have a short video. I don't see any big videos, but basically they have machines that launch big old pumpkins. And it's like a competition where these people build things from catapults to air cannons, and they'll launch these pumpkins as part of their competition. So, you know, maybe I'm guessing it's something like this. So, yeah, okay, it's quite forceful. So I guess it makes sense. All right, here we go. Next question. A squirrel is 24 feet up in a tree and tosses a nut out of the tree with an initial velocity of 8 feet per second. The nut's height, h, at t seconds in time can be represented by the equation h of t negative 16t squared plus 8t plus 24. So again, we know that he's 24 feet elevated, in an elevated position 24 feet up. So that's already in the formula, 8 feet per second. So again, this middle one is the velocity. So we know that that is accounted for, so we don't need to really plug in anything else. The first number, negative 16t squared, is again, how fast something falls in Earth's gravity. So that is the, basically gravity, the force of gravity pulling on something. So yesterday we worked on a problem where we were calculating how fast something will fall on the moon, and it would fall much slower because there is less gravity. So this formula is already translated for us. We don't need to do anything really. And let's see, let's read our question statement. If the squirrel climbs down the tree in 2 seconds, does it reach the ground before the nut? Okay, so let's see. Just to draw a picture, let me go ahead and draw a tree. And it doesn't have to be fancy. Okay, I'm just drawing just for fun, really. Let's see, there's a branch coming down here. Some leaves on it. And there's our squirrel. Now let's make him look more squirrel-like. Got a big old tail. And a little head. Yeah. So anyway, so it's thrown upwards with a little bit of force. I don't know how, well, wouldn't really know exactly how that works out. And he throws it and then decides to immediately climb down. So we're going to see if he can climb down faster than the nut can go up and then back down onto the ground. So to do this, we need to calculate the zero. Okay, so when the ground is zero, then that's when, well, the ground is zero. The elevation compared, you know, for its flight is zero, because once you hit the ground, you can't really go any lower unless there's, well, I guess if there's a canyon, but then the ground would still be at the bottom of the canyon. All right, so let's go ahead and see what we can do with this. So what kind of, which strategy could we use for this one? And yesterday I said that there were some strategies you should try. Oopsie. Square root property is probably one of the ones that you should try first, because if you have only two numbers and no b value, square root property is one of the better ones. And then factor, so this is two ways. Remember, we have reverse distributive and the double bubble method. And then let's see, after factoring, we could try completing the square, but that's actually kind of a rare one to use. I don't really see that one used all that often. And in this case here, we have our trump card. Actually, that's not really a good word to say anymore. You know, well, it used to mean like the thing that you could use to basically turn something in your favor, but I don't know if I should say that. It sounds too political. I don't know, the big hammer, the one tool that will get the job done, but it's really not the best one because it's like, again, it's like a big tractor. You know, if a little tractor can do it, use the little tractor, okay? But the big tractor, it will do anything. It'll knock down any wall. It will dig any hole. It will, you know, flatten any ground. But the problem with the big tractor is that it's big. It's lumbering and heavy and probably uses up a lot of gas. So the companies don't really want to use the big tractor if they don't have to. So that's where the quadratic formula comes in handy. So I'm looking at this here, and I have very large numbers on the sides. This means I may not be able to find factors that work out, because if I have, you know, factors of 16, there would be 1, 2, 4, 8, and 16. So there's a lot of different factors I could use with that one. 24 has even more factors. It would be 1, 2, 3, 4, 6, 8, 12, and 24. So there's a lot of numbers that we could use in combination with this. So them both put together, we're looking at maybe 20 to 30 different combinations of numbers. So I'm going to say factoring is off the list. Square root property, we have a b value, so that's not going to work. Completing the square, okay, we could get it to work, but there's going to be a problem with the a value here. So if you can't really factor it, then we're going to have to go to quadratic formula. So the problem with quadratic formula is that a lot of, well, it's worth it if you can remember it, but remembering it is a bit of a hassle. So any chance I get, I'm going to go ahead and try to remind you of that formula. And I haven't got all of it out just yet because it is a bit of a, there's a bit of stuff going on with it. So let me go ahead and write this down. So that's negative b plus and minus, because we also have to consider the minus over the square root. I'm sorry. I was writing something in. Anyway, negative b plus and minus the square root of b squared minus 4ac all over 2a. Not bad. But again, you have to remember it. If, like, say you're taking a test, quadratic formula is not going to do you really any good if you don't remember it. So let's go ahead and start plugging things in. Negative 8 plus and minus the square root of b squared. So this is 8 squared minus 4a, but we actually, I don't need to put a in there. I need to put the number that is in the a position. And 2 times a, so this would be negative 16. All right, so we got quite a lot of stuff going on. So I'm gonna go ahead and use the calculator. And we're gonna calculate the discriminant. That is all the stuff underneath the radical. That's the b squared minus 4ac. All right, so we have 8 squared is 64. All right, that's easy. But what we don't know is negative 4 times negative 16 times positive 24. All right, so we have two negatives. So we know that's going to cancel out. So that's great because I don't really want to use my negatives if I don't have to on this calculator. So 4 times 16 times 24 is going to be 1,536. And again, this is plus. It was changed to a plus. So that means plus 64. So that's going to be 1,600 or 1,600. So all this under here, so again, 64 plus that 1,500 number. And what is, okay, well, actually, you know what? While we're at it, I'm going to go back to the calculator. And we're going to take the square root of this number, which is 40. Okay, not bad. So 40 over 2 times negative 16. So this would be negative 32. All right, so there's two possibilities. So 40 minus 8. or actually, hold on. Let's do them in order. So -8 plus 40. So this would be 32 over -32, which would be -1 second. All right, but again, remember, we gotta ask ourselves, does that make sense? Is it possible for a nut to fall out of a tree and hit the ground in -1 seconds? Nope, that's totally preposterous. Okay, so that's not gonna work out. Let's try the other combination, and that is to add it, or we did add it. No, wait, minus. So we got to minus it this time. So in this case, it would be -8 minus 40. So that would make two negative numbers. So two negative numbers will combine to make a larger negative number. And we end up with a fraction. And anytime you have a fraction, try to divide it. And if it won't divide, reduce it. But in this case here, well, we're looking at seconds, and seconds are usually measured in decimals. So this is one of those times that would be really best to use decimals, even if we don't have to. So 48 divided by 32, and again, they're both negative, but I know negative divided by negative will be positive. So this gives us positive 1.5. So 1.5 seconds. So is this our answer? Well, okay, if the question was, how long will it take for the nut to land on the ground? Then that would be our answer. But in this case here, it is a solution, but we need our answer. And because the question is, will he manage to climb to the ground before the nut impacts the ground? In this case here, the answer is no. Nope, he does not manage to climb down before you know, he's not going to be able to catch it or anything if that's what he's trying to do. So there you go. The answer is no. Okay, there we go. And again, we don't have that many to go through. We're pretty much near the end of it already, so we're about halfway when we get to this problem. A quarterback throws a football from a height of 6 feet with an initial velocity of 20 feet per second. The height of the ball h in time of t seconds can be represented by this equation. If the ball is caught at 2 feet, find the range of the function. Okay. So we are looking for the range. This means we are looking for y values. So domain, if you remember yesterday when we were talking about the types of things between domain and range, right? So in this case here, if I have my graph, and it says he's elevated from a height of 6 feet, which is kind of weird because football is usually played on a flat surface. I don't know, maybe he's throwing it from bleachers or something as part of an exercise or something. But either way, he throws it from 6 feet up. Or maybe this is not actually an elevated position because maybe the player himself is 6 feet tall, and when he throws it, he probably throws it from his head level. Maybe, I don't know, or maybe he's a little bit shorter than 6 feet, but he kind of throws it overhead or something. Yeah, that actually makes a lot more sense. So I'm gonna go ahead and go with that explanation. He is roughly 6 feet tall and he throws it like that. So again, back to my explanation, x-axis is time. So again, that's how far it is. Now there's a bit of a weird thing because when I talk about this, I don't like throwing too much information at people all at once. But this is not actually the path of the ball, okay? This is like time, all right? This is time, not necessarily where the ball is, because I know it's easy to look at this and say, okay, well, that's the path of the ball. But you can throw something straight up, and it doesn't go anywhere, and it would still come back down in the same time as if it were to be thrown sideways with that same amount of force, well, upwards force. So this is not, again, distance, it's time. The y-axis is the height. So this tells us that we are looking for the height of the football. So for this one here, we're going to have to work out a little bit of, okay, let's see, what can we do? Well, we want to know what the maximum height is. We want to know what the maximum height is, and we also want to know what the minimum height is. Now, there's also another clue here, and that is the football is caught at 2 feet above the ground. So he probably has a fellow player. You know, the ball comes a little bit lower, and he probably dives for it. All right, but that's when the ball stopped its normal path of falling. And while I'm at it, you know, I might as well just draw the football. So we know that it's going to be here. So we already know the bottom value of this. So before we do any work, we can actually get one of the answers. So the minimum falling path is 2 feet. But what we don't know is the maximum height. The maximum height is what we do not know. So that means we only have one thing to really look for, and that is the maximum height. And again, we need our axis of symmetry formula. So let's go ahead and put negative 20 in here. So that's, it's positive 20 in the formula, but we need the negative number, and and put this in here. So negative divided by negative. So at this point here, if you're looking at this, you know these two are going to multiply to be a negative number. But I'm going to go ahead and again, if I can get rid of the negatives, I will try my best to get rid of negatives whenever I can. Now I'm going to go to the calculator and go 20 divided by 32. And this is 0.625 seconds. So that is when the ball reaches it. And now again, when you're dealing with something that is thrown by a person, usually people are not very powerful. So, you know, this ball spends only about a little more than half a second to reach its maximum height. Okay, I know if you watch a lot of ESPN sports, it's easy to think that a ball stays in the air longer than that because they always play the playbacks in slow motion. Okay, but really things fall pretty quickly. All right, now we got to plug this back into our formula. And again, by plugging this number back in, we are asking the formula, we're asking the function, where is the ball in 0.625 seconds? So I'm going to plug it in and let's go ahead and work this out. Now I'm going to go ahead and use my calculator, but I'm not going to switch screens in this case here, just so I can go a little bit faster. And it's not anything, I'm not really doing anything that's all that different. Just the usual stuff. Okay, there we go, I got it. Let me go ahead and show what we have. So this is going to be 12.25 is the maximum height. So the ball reached a maximum height of 12.25 foot. So that's about 12 feet 4 inches. 12 feet 4 inches. And that means, okay, let's see. And the ball doesn't really need to go very high to go very far, because again, this formula does not account for sideways force. If you watch most games of football and for the pass plays, they usually launch that ball sideways. Okay, they're trying to get that ball past as fast as it can with as little time in the air as possible. So there's not a whole lot of upwards force in the football if they can avoid it, because you don't want to have a high arc and give the opposing team a lot of time to view the ball in air and try to intercept it. So again, there's a little bit more going on with these kind of questions than you might think. All right, let's go ahead and move on to the next one. Oh, let me go ahead and box this up because this is our answer. The range, or the height, is between 2 feet minimum, right, and 12.25. And again, it's not, I mean, the ball probably will hit the ground, especially if somebody dives after it, but that is the minimum path in its free fall, in its flight motion. Okay, sorry. Oh, and also, let me go ahead and put the equal signs on here. Actually, I almost forgot that because it did go to this height, and it did go to that height. Since it did go to those heights, it is or equal to those heights. Okay. Similar question to one of the ones we had in a previous lesson. A penny is dropped from the Statue of Liberty, the top of the Statue of the Liberty. A penny is dropped from the top of the Statue of Liberty, which is 305 feet tall. Wow, that's not that high at all. I don't know, in my own mind, it always feels like it's taller than that. Anyway, the height of the penny, h at t in seconds, can be represented by this equation. After 4 seconds, how much further does the penny need to travel before it hits the ground? Okay, so let's see. Now, we don't really need to draw a picture. And even though I could probably draw a very good Statue of Liberty, similar to the squirrel, you know what? I don't really need to do that. Let's go ahead and make a stick figure. It looks something like this, and I'm just going off the top of my head, and it's like got a book. Yeah, there we go. And then a dress, I think. Was it a dress? I think it's a robe. Actually, that's not bad. And it's even green too, my usual color for drawing. It used to be copper color, but now it's green. All right, so let's see. There is no upwards force in this equation. So this is one where it's not thrown upwards before it falls. Okay, so it's just sort of pushed off the side, or someone just sort of puts their hand out and then drops it. So there's no upwards force. So this means that it starts its motion already at its maximum height. So there is no B value. This one might be a good one for completing the square, but actually we may not need to, because I don't know how long it's going to take, but we just want to know where it is in 4 seconds. That's all we want to know. We don't want to know how long it takes to hit the ground. We don't need to know the maximum height, or when the maximum, well, we know maximum height would be 0 time, and we know the maximum height is 305. But again, we want to know where the penny is at 4 seconds. So that's what we're going to do. We're going to go ahead and plug into the original equation 4. So by doing this again, we are asking the function, okay, so where is the penny at 4 seconds? So 16 times 4, that's 16, 32, 64. So this is negative 64 plus 305, and 305 minus, oh wait, no. I forgot to square it. Duh. 4 squared is 16. 4 squared is 16. So this is 16 times 16, which is 256. And I remember that because, well, I grew up in the 80s, and well, at least around me, I never saw colored computers, but the first color computer I saw was a 16 color, and then they came out with 256 color, and that was like mind-blowing at the time. You're like, oh man, the future is now. I think most computers nowadays have like thousands or even millions of colors, but there were 16 colors and 16 shades of each color. anyway, so there we go. We know that the penny is 49 feet off the ground in 4 seconds. Well, maybe I could put this as an ordered pair because this is kind of like a graph. So in 4 seconds, when x is 4, y is 49. All right, now we need to know when it will hit the ground. So how do we know when the penny will impact the ground? So we have to set h equal to 0. So h is this outside number here, all right? Because again, 0 is the ground. So 0 equals negative 16t, and it says when will it hit the ground? Okay, so we're asking, it doesn't say it in here, but we are asking when will it hit the ground? So we need to know when it will hit the ground. All right, so this means we don't know what the time is because we're asking for the time, right? Because if you're asking for something, that's one of the things you don't know. It's one of the things you don't have. So I'm thinking we could use completing the square, and I'm gonna, excuse me, I'm gonna use completing the square because, well, I'm just gonna use it whenever I can. Okay, so in this case, we have no b value, which is always a good time to use completing the square. And I'm going to add 16t squared to both sides. So that's going to cancel it off of here. So 16t squared. I said 16. And I'm going to go ahead and divide both sides by 16. So 305 divided by 16. And that would be 19.0625. There you go. And I just did that off camera with the calculator. And again, I just divided 16. Let me go ahead and show my work. Divide both sides by 16, and that cancels the 16 here. So we end up with this, but we still need to solve it. We still got to get this t by itself, and that means we got to get rid of this square. So go ahead and take the inverse, the opposite of square, and that is square root. So take the square root of both sides, and we should be able to get it. So let me go ahead and move back over here. So again, I did this off screen, and I need to take the square root of it. So we have 4.366, and I'm going to just go to here because there's a 0 right there, which means I don't need to round it. And I'm going to just go to 3 decimal places because it looks, in this case, it looks like what we need to do. So it's going to be a little bit different it's going to be a lot more accurate the more decimal places you have. But, you know, I mean, if you're counting a penny coming off a building, you probably wouldn't really say 4.36 for 4.366 seconds. Okay, unless you had like a stopwatch or something, you wouldn't be that precise. Okay. All right, so we know the penny is at 49 feet. How much further does the penny need to travel before it hits the ground? So we know where the ground is. So here is the ground. Okay, and you know what? I'm going to go back over to the calculator here. And I'm not, let me see. Okay, so I've got my graphing utility here. So I'm going to go ahead and punch in the equation that we were working with. But instead of t, I'm going to replace it with x. And there we go. So this is our path of the penny. And I'm going to show you how you can do this with a, so there we go. Like I said, it's this is the top of the statue. So 305, and again, it's falling. There's no upward motion to begin with. And what I'm going to do is I'm going to plug in x equals 4. So by doing this, again, I'm asking where is the penny at 4 seconds? So this is why there's a bar here at 4 seconds. I'm gonna zoom out to go a little bit faster. In fact, let me just fast forward this. And I can look for where the lines intersect. So where is the penny at 4 seconds? There it is. So at 4 seconds, it is 49 feet off the ground. Okay, so and if we want to know where it hits the ground, so we're following the blue line. So the blue line is the path of our penny, and it hits at 4.366 seconds. So a little bit over a few seconds, right? So it's only 0.3 seconds, which is about 1/3 of a second to hit the ground. Now you can use graphing utility to check your work, but you don't really, I would not suggest it to actually do the work. And there we go. So we know where this penny was after 4 seconds, and we know how much further it needs to go. It needs to go 49 feet off the ground. And how much time it hits the ground? 4.366 seconds. All right, let me see. So that is it for today. Let me know if you have any questions. I'll be around for a little bit, but until next time, I will see you later. Bye-bye now.